talking about biological neuron and the transition, like from how artificial neuron has been developed from biological neuron, and then how the functioning of both of these neurons are same. Okay, so if we look at biological neurons, so there are dendrites like through which like electrical signals gets accumulated inside this neuron from other lot of neurons. Okay, so there can be a lot of neurons from where these signals might be coming inside this neuron through a dendrite. So it's get accumulated inside the cell body, and if the sum of the electrical potential of this electrical signal is greater than threshold, then this neuron is said to be firing. So that means like it will transmit some signal to another neurons through axon dendrites. Okay, so again the signal which it transmit can be of any number. I mean the neuron which is receiving this signal which this neuron is transmitting can be of any number. So that is based on what exactly the function of this neuron is like. So it depends on its functioning, like if it is for hearing, speaking, seeing. Okay, so if we look at the mathematical framework of this biological neuron, which is known as artificial neuron. So if we look at history, then in 1943, Warren Mikulik and Walter Pitts came up with this architecture for the artificial neuron, which was known as Mikulik-Pitts neuron. And it was like more constrained or limited to Boolean functions. Okay, like defining the Boolean function. So it was pretty much it can this artificial neuron can like Mikulik-Pitts neuron was able to was trained to like function any of the Boolean functions. So that's why it came into more focus, but it was not flexible for any other kind of nonlinear functions. So that's why in 1958 Frank Rosenfeld came up with perceptron. So which was not limited just for a Boolean function, but it can even solve a real valued problem. Okay, so if we look at this diagram, then this is a Mikulik-Pitts neuron. Okay, so and like perceptron is nothing. It's just an improved version with the weights in this architecture. Okay, and these weights and the theta, this is the threshold, and this threshold is exactly what we saw in the biological neuron, because this accumulation inside the cell body, if it exceeds the threshold, then only this neuron will transmit the signal. Otherwise this neuron won't transmit any signal. Okay, so in a similar fashion, even the summation from all the signal coming through this input should exceed the threshold. That's only in that situation our output will our neuron will get fired. So that means our output will give some output. Okay, otherwise it's not going to give any output. Okay, so if we look at Mikulik-Pitts neuron, so there is no any weight, so that's why summation of all the if I is 1 to n, then if it's greater than this threshold, then only our neuron will get fired, so our output will be 1. Okay, otherwise it would be 0. And if we look at this is Mikulik-Pitts neuron, and if we look at perceptron, then it's more or less same, but just weight is added over there. Okay, and if it is greater than threshold, the rest of the framework is same. Okay, and okay, so Okay, so exactly what so now like let's see like what exactly these weights are in biological neuron, what exactly these weights, because threshold we know it, like this because these signals have some potential voltage, so we can add all this potential of this voltage and then just see the summation, if and we can see there's some real value, and then if it's greater than some threshold, then we can see this thing, right? Like what is the threshold thing. And firing, like exactly this firing is like sending some signal, otherwise it doesn't send the signal. So in the similar fashion, like we are seeing, either if this neuron gets fired, then we'll be getting 1, or if otherwise we'll be getting 0. So that's that is even exactly similar what we see in biological neuron. But exactly what is this weights? And these weights we are not able to see. I mean, like we are not able to like correlate exactly what is in what form is there this weight, right? So now so there is something called synaptic strength. Okay, so this signal from this between two neurons. So if there is some other neurons and then this signal information gets flow inside this dendrite with something called synapse. Okay, and in a similar fashion, the signal transmitted from this neuron goes to some other neurons through through the same phenomenon known as synapse. So this synapse is nothing other than just a connection between the neuron which is created because of some electrochemical reaction. Okay, so there are some ions and which are like electrochemical in nature, and then this flow, they will flow from one neuron to another. So that is how synapse is created, and this is called synaptic gap because I mean there is a gap between this axon terminal and dendrite between of two different neurons, and this ions has to pass through this gap. Okay, so this transmission can be like weak or strong. Okay, so if it is weak, then this information won't be getting into another neuron, and so that means that neuron is not transmitting anything. And if this synaptic strength is strong, then that means these ions, these electrochemical ions, are getting into the passing through the another neuron. So that's how our information is getting transmitted from one neuron into another neuron. Okay, so this synaptic strength so we have modeled this synaptic strength in this artificial neuron as a weight. So these weights are the nothing than this synaptic strength, like what do we see in biological neuron. Okay, so if we see at if we see at this biological neuron, or let's say if we see at this artificial neuron, this weight will get tuned, or this weights will be learned through data. Like with observation of the data, this our neuron will these weights will be trained or will be learned, and that's how we can make this neuron work in for different functions. Okay, and if we look at a biological neuron, it's about repetition. Like if we see something, like if we see some image again and again, so that's is going to get stored in our brain, and whenever we see that image again, then that neuron gets fired. So that's how our this because of this repetition of this process again and again, this synaptic strength gets more stronger. Okay, so that means like if we look at artificial neuron, that's showing that our weight is becoming more peculiar. Okay, so and one more thing, like so here I'm showing is a axon terminal, and here as a dendrite. Okay, because and when we see at this biological neuron, like our information flow through the axon and then to another terminal through axon terminals, and information flow inside this neuron through dendrites. So So information is like passing from axon terminals to the dendrites. So dendrites will be something like from which information will be incoming, and dendrites will be something information will be outgoing. Okay, so in similar fashion, so here I'm just trying to show that information is coming inside this neuron. So that's why it's showing here axon terminal, because axon terminal is where information will go outside, and dendrite will be something information will be coming inside. Okay, so if so that's why information flow is in this direction. So if information is in opposite reverse direction, then this is going to be axon terminal, and this is going to be a dendrite. Okay, so there is one more we can like develop electronic circuit for this neuron, artificial neuron, like so if we again see, like look at the artificial neuron, then these inputs are like same. Okay, and the weights, and these weights are modeled as a variable resistor. So I mean this weight can be tuned as per our neuron functioning. Okay, so all these are learnable parameters. Okay, these are learnable parameters, and then y will be again here either 1 or 0 if some signal comes gets transmitted through this I mean if this transistor get high, then I will get 1, and then if it's not, then it's will be getting 0. Okay, so again in a similar fashion, all the signals coming inside this will be added here. Okay, that is exactly, if we look at a neuron, so in the beginning all the signals are getting added, input are getting added, accumulate. Okay, and once this sum, okay, like once this all signal gets added up, then if it's greater than some threshold, okay, if it's greater than some threshold, so that threshold can be like modeled here as again as some variable resistor. So if that sum is like again so it means like this base voltage is greater than some voltage, then only this transistor get activated, otherwise this transistor won't get activated. Okay, so that can be like controlled from this resistor. Okay, so if the sum is greater than theta, then this transistor get high, and then that's how our signal will pass through our and we'll get 1 over here, some signal is passing over here. But if it's not greater than threshold, then it's not going to get this transistor is not going to get turned off, so turn on. So that's how the current will flow from here to the ground. So that's just trying to show that our neuron is not getting fired. So yeah, so this is how we can model even this biological neuron or our artificial neuron in a more electronic circuit. Okay, so